So the focus of this video is going to be determining whether or not a molecule is polar, So we talked about in the previous video polar bonds. So let's go over that and how that is different from a polar molecule. Okay, so polar bonds is always going to be what we call the difference between the electronegativities. Okay, so that is going to be, again, the table that you will always have available to you is this electronegativity table. Okay, so when you subtract those two numbers, that's going to determine if it's a polar or non-polar bond. So again, your table has those ranges, and again, these are just general ranges that we are going to be using to determine if it's non-polar or polar. And if you have a really big difference greater than 2, then we're going to consider that more of an ionic phenomenon or an ionic bond rather than it is covalent. So that is how we determine if it's a polar bond, just by the electronegativity and subtracting the two numbers. Pretty straightforward. So what is a little bit more tricky is polar molecules. So again, we're talking about the whole molecule itself. And I'm going to give you essentially the rules, and then I'm going to kind of explain it through a couple examples. So in order for the molecule to be polar, the shape has to be polar. So there are certain shapes that tend to be polar, certain shapes that tend to be non-polar. And then there are going to be, again, for instances or places where something that is non-polar becomes polar. And so that's going to be what we kind of discuss. So generally speaking, polar shapes are going to be the trigonal pyramidals and the bents. And that is due to the fact that you have lone pairs on those two shapes. So trigonal pyramidal has one lone pair, the bent shape has 2 lone pairs. So that's going to be how we kind of differentiate their essentially the shapes. Non-polar shapes are going to be linear, trigonal planar, and tetrahedral. So those are going to be considered the non-polar shapes. So let me go through a couple examples to kind of help you as to how you figure this out. So again, I'm going to pause the video here and then you're going to see something in a second. So I'm going to work a couple examples for you to get an understanding of this idea of polar molecules. So the first molecule I'm going to draw is CCl4. So again, please stop the video and write this down. I'm just trying to speed up some of the videos here by doing some pausing on my own. So I have carbon in the middle and 4 chlorines attached, all single bonded, and I have lone pairs around the chlorines. So since that middle atom, the central atom has 4 bonds, okay, and no lone pairs, that is a tetrahedral. I have a bond angle about 109. And again, when you draw these molecules, they don't have to be drawn according to the bond angle being exactly 109. So again, we're talking about polarity here. So when I look up on my table, okay, I look up carbon. Carbon has an electronegativity value of 2.5 and chlorine is 3. Okay, so chlorine has the bigger number, so that means the electrons are being pulled in that direction. So draw yourself a dipole arrow. So again, the dipole arrow is always going to point towards the one that is more electronegative. So then I subtract the two numbers and I see that my difference is a 0.5. So I have a polar bond. So if I ask you if there's a polar bond in this molecule, you're going to say yes, it is a polar bond. But the bigger question is, do I have a polar molecule? So again, this is my model of my tetrahedral, again, going out at 109. So I'm going to kind of refer to that. So I'm going to draw my dipole arrows on my molecule here. So each one of these bonds, all of the electrons are being pulled towards the chlorine, okay? And sometimes it gets confusing as to where your bond is or where your dipole arrow. So sometimes I don't like you drawing too many dipole arrows because it does get a little confusing. So all of these pulls are going out at a 109 degree. Okay, so I want you to think of it kind of like pulling on a rope. Okay, if I had a rope and the knot was in the middle and I had 4 people pulling out at 109, again, say we could do that, all of the pulls essentially would cancel out, okay, because everybody is pulling the same amount and everybody's pulling at the same degree. Okay, so essentially these are all canceled out. And if you had some physics background, these are like vectors. Okay, so we're kind of canceling out. So we have what we call no net pull on these dipole arrows. There is no net going in one direction or the other. Okay, so everything cancels out. okay? Because everybody is pulling equally, everybody's pulling it the same. So that makes it a non-polar molecule, okay? And that is why I said that these particular shapes, tetrahedrals, tend to be non-polar, because if they all are pulling out at the same amount, you essentially have a canceling effect. Where it becomes polar is, what if I had something else attached here besides chlorine? What if one of these happened to be fluorine? Well, since fluorine is going to pull more, you're then going to make it a polar molecule, okay? But if everything is the same on that central atom, it's going to be a non-polar molecule. All right, so let's look at our friend water here. Let's look at our friend water. So water is what we call a bend shape, okay? About a 105, 104.5 degree angle. Okay, so here is my water molecule. There is my water molecule. And when I look up oxygen, again, it has a 3.5. My hydrogen is 2.1, so I have 1.4. So I have a polar bond in this molecule. But like I did before in my previous video, the dipole arrow is going to point towards the oxygen. It has the bigger value of electronegativity, okay? So if I do it on the actual molecule, okay, all of those dipole arrows are pointing towards oxygen, okay? So if I have my model here and my arrows are my fingers, they are pointing towards the oxygen. They're pointing towards the oxygen. So they're all pointing in one general direction. So the overall pull is going towards the oxygen. So I could draw what we call a dipole arrow for the molecule, because all of those pulls are going in one direction, okay? So this is all, the pulls are all in one direction. So they don't cancel out. So this makes it a polar molecule. And you better know water is a polar molecule. That's going to be key in some lab stuff that we do as well. Okay, so water is a polar molecule. Water is a polar molecule because the net pulls do not cancel out. The net pulls don't cancel out because of this bend shape, because of that bend shape. All right, and what about NH3? What about NH3? So I'm going to pause the video and you're going to see it drawn for you. So ammonia, NH3, is a trigonal pyramidal, So here is the model of it. So again, trigonal pyramidal, it sits up. I have a lone pair on the nitrogen. That's what you can't see here. And I have three bonds to hydrogen, So I have that lone pair on the top. Again, the bubble you see on your sheet, trigonal pyramidal about 107. So if I look up nitrogen, it has electronegativity value of 3, hydrogen is 2.1. So when I subtract them, I get 0.9, I get a polar bond. But what I want to know is, what about the molecule? What about the molecule? Is that going to be a polar molecule or not? So this one is much harder to do with my fingers, because I need like 3 good fingers here. So they're all pulling towards the nitrogen. Okay, so nitrogen really is going to want the electrons more. So all of the pulls are naturally going towards the nitrogen. Okay, so all of the pulls, and it's harder to draw because, again, this is a flat surface, so it's kind of hard to do it correctly. So all of the pulls don't cancel out like before. So this makes it a polar molecule. But recognize both of these shapes, okay, trigonal, pyramidal, and bent, have lone pairs. And so one side is always going to be the bonds and one side's always going to be the lone pairs. So whenever you have that unevenness or asymmetry in the molecule, meaning bonds versus lone pairs, you're always going to have a polar molecule, because you can't cancel everything out, because you're always going to have one side's going to be the bonds and one side's going to be the lone pairs. So that is why it tends to be that any lone pairs is going to make it a polar molecule. All right, so let me draw one more, and that's CO2. That is CO2. So the last one I'm going to draw for you is CO2. CO2 has 2 double bonds. That's the only way carbon, when you have 4 valence electrons and then 6 times 2, that's the only way this will work. You have 2 lone pairs on the oxygens. So oxygen is more electronegative than the carbon, 3.5 to 2.5. So when I subtract those 2 numbers, I know that that's a polar bond, okay? Again, polarity of the bond is just going to be the subtraction. But this one lends itself to a very nice discussion. This one kind of explains that whole pull thing. So if I have a traditional tug of war and I have 2 people pulling on a rope, and they are pulling equally. So they are of equal strength. That knot in the middle where that rope is not going to move, okay? Because each one of these is going to cancel each other out. So this force going in that direction, that vector going in that direction, cancel each other out. So this cancels out. So I have a non-polar molecule. So think of a tug of war kind of situation. So since these cancel out, linear shapes, okay, being at 180 are going to be non-polar. Now, if you have something attached to it and it is different, you are going to make it polar. So this is only if that central atom is attached to the same things on both sides. If you have something different on one side or the other, then you're going to make it polar. Like, so for instance, we have, let's say beryllium. Again, beryllium is just an easy one because it only makes 2 bonds. If I had fluorine on one side and chlorine on the other, okay, and fluorine has electronegativity difference of 4 and chlorine is 3, fluorine is going to be a bigger vector than the chlorine. So this is going to be a longer arrow as a way for you to kind of see that. So it is a linear shape, but because the fluorine is different than the chlorine, I then have what we call a polar molecule, even though traditionally that shape of linear is going to be non-polar. So anytime I have something different attached, that's going to make it polar. So polar molecules just mean one end of the molecule is positive, one is negative, okay? So going back to my examples here, so if I look at my water molecule, okay, hydrogen is slightly positive and oxygen is slightly negative, positive and negative. So I have one end that is positive, one end that is negative. It doesn't mean it's a complete +1 or -1. It just means I have positive and negative. And a dipole, again, is a molecule that has a negative and positive charge. So that dipole arrow that I've been drawing that you can draw on the molecule itself can represent essentially that you have a polar molecule. So again, just to sum up, okay, your polar shapes are going to be the ones that have lone pairs, okay? So anytime you see a lone pair, that's going to make it polar. Non-polar shapes are going to be these traditional ones unless I have something different attached to that central atom.